Let us try to understand about clock group. So coming to clocks and clock domains in digital design. When a design has more than one clock, the timing of the design depends not only on the frequency of the clock, but also on the relationship they share with each other. Here relationship is nothing but phase relationship. Types of clocks based on relationship. There are two types. One is synchronous clock, another one is asynchronous clock. So synchronous clocks share a deterministic phase relationship. More often than not, they are derived from same clock source. Here clock source is nothing but PLL, that is phase lock loop. Since the phase relationship is fixed, their timing analysis can be handled directly by STA tools, that is static timing analysis tools. Now coming to asynchronous clocks do not share a fixed phase relationship. They are typically generated from different sources. In such cases, signals transferred between two domains are considered asynchronous clock domain crossing. These crossings must be handled carefully using synchronizers or FIFOs, that is first in first out, to avoid metastability issues. So this is about types of clock, that is synchronous and asynchronous. So synchronous is something which is coming from the same clock source. Asynchronous clocks are something which are coming from different clock sources. Now let us see what is meant by this clock domain. The section of the design derived by a particular clock is called as clock domain. Each domain is analyzed with respect to its own clock. When signals transfer from one domain to another, the nature of the clock, that is synchronous versus asynchronous, determines how timing constraints are applied. So how many number of clocks that you are using, that many clock domains will come into the picture. That is, if you are going for C1 and C2, which are coming from two different clock sources, then C1 is one clock domain and C2 is another clock domain. So let us see this example. Consider two clocks C1 and C2. So here I am going with a figure which is having two flip-flops, F1 and F2, and here F1 is driven by clock C1 and F2 is driven by clock C2. If they are generated from the same source, they are synchronous. If they are generated from different sources, they are asynchronous. So simply this figure is something which is asynchronous. Why? Because here these two clocks are generated by using two different sources. So that is why it is called as asynchronous clock domain crossing. So here clock domain crossing is something like, if you see here, this is one clock domain and this is another clock domain. And if a data is traveling from one clock domain to another, so here this is the combinational path that is present between C1 and C2. So because of this, we may get some CDC issues. So in order to overcome this kind of things, we need to go for synchronizers, or else we need to go with FIFOs. Timing impact of multi-frequency clocks. In multi-clock designs, the frequency of each clock affects how fast signal propagates within that domain. More importantly, the phase frequency relationship between different clock determines whether signals crossing between them can be timed by STA or need to be treated as asynchronous CDC. So let us try to understand what is meant by setup and hold timing check. So as we have seen in the previous figure, that is 7.1, it contains two flops, F1 and F2. Here F1 is called as launch flop and F2 is called as capture flop. And these are the definitions for setup time and hold time. So the minimum time before the active clock edge when data must be stable is called as setup time. That is the minimum time for which data should be maintained constant before the active edge of clock is called as setup, and after the arrival of clock the data should be maintained constant, that is called as hold. Both checks ensure correct data transfer between sequential elements. So let us try to understand it by means of an example. So here I am taking two clocks F1 and F2. F1 is driven by C1, F2 is driven by C2. So here TF is nothing but clock to queue delay of launch clock. So from clock to queue it will take some amount of time, that is represented as TF, whereas TC is nothing but combinational delay. So here TC is called as combinational delay. Setup requirement of capture flop F2 is represented as T setup. Hold requirement of capture flop F2 is represented as T hold. So here we will be calculating between D pin and clock pin, setup and hold. Generally we get these values from the dot lib, and T period is nothing but time period. Now here we need to understand the terminology called as arrival time and required time. So arrival time is something which is from clock to queue delay followed by this Q2 input pin of flop 2. That is TF plus TC will give arrival time. So arrival time is TF, that is clock to queue delay followed by combinational delay will give T arrival. So here in order to understand setup and hold, you need to know what is the formula for the setup. So generally for setup required time should be greater than arrival time, or else arrival time should be less than required time. However, both are same. So arrival time we know that TF plus TC, whereas required time is something that is total time period minus T setup. That will be taken as the capture flop. So here this T period minus T setup is required time. TF plus TC is called as an arrival time. Next, coming to hold. Hold is something where arrival time should be greater than required time. So arrival time should be greater than required time. So arrival time is common only. So arrival time is nothing but clock to queue delay, that is represented as TF, plus combination delay, that is TC. So arrival time is TF plus TC, whereas here required time is something which should be taken only as T hold. Whereas in case of setup, it will be total time period minus T setup. Next, coming to the example case 2, clocks with skew. So skew can be positive skew or negative skew. So here in this particular waveform, you are not seeing any skew. Why? Because it is starting at 0 nanosecond and it is also starting at 0 nanosecond. Whereas skew is something like this particular capture flop clock will be pushed either forward or backward. If it is pushed forward, means it is pushed towards the right hand side, then it is called as positive skew. If it is pushed towards left hand side, then it is called as negative skew. So I will be explaining this particular concept in detail in the upcoming videos. As of now, you just go through this particular slide. The only difference that you will be seeing is, apart from total time period minus setup, you'll be adding that particular TZ, which is nothing but skew. Similarly, for hold also, you'll be adding TZ, which is called as skew. And here, this is nothing but a launch clock time period followed by TF, which is called as clock to queue delay, and TC is nothing but a combo delay. Launch clock time plus clock to queue delay plus combo delay. This together it is called as an arrival time, should be less than required time. This is complete thing is called as required time. And same thing is applicable for hold, but only thing is here in the previous example, we have seen only T hold, but here we are adding this Q hold. Next, coming to multi-frequency. So multi-frequency is something like C1 will be operating on one frequency and C2 will be operating on another frequency. That is, it can be slow fast or else fast slow. So you can see this example here. Here, suppose if you take this as C1, it is fast clock, and if you take this as C2, it is slow clock. Whereas here, if you take C1 is slow and C2 is fast. So here you are having a time period of 10 nanosecond. Here we are having a time period of 15 nanosecond. Similarly, here time period is 15 and here time period is 10. From 0 to 10. This is nothing but a time period. So in the upcoming videos, we'll see like how to calculate this hold check and setup check. Like why it is only at this particular edge, why not here and all. We'll see in the upcoming slides.